Okay, this is a discussion over antiderivatives. So it's kind of our first step into a concept called integration, which is essentially one half of calculus, a branch of calculus. So antiderivatives are essentially what the name says and what it implies. It is the opposite of doing a derivative. Okay, so the way that we're defining an antiderivative is that it is a function that is an antiderivative of another function if the derivative of the antiderivative is equal to f. So essentially what we're doing is we're working backwards. The one thing that you want to be careful with when you are finding antiderivatives is that you want to make sure that you always add this plus c. And what that plus c is, it is an arbitrary constant. And if you think about taking derivatives, anytime that you take a derivative of a function, if there is a constant term to that function, when you take the derivative of that constant, it goes away, right? The derivative of a constant is 0, so it disappears. So if I'm working backwards, I have to say, well, there could have been a constant added to this, where when I took the derivative of it, it then went away. Okay, so we're going to look at 3 examples really quick, and then I'll get into some rules here at the bottom of these notes. So if f is cosine of x, I want to find the general antiderivative of that. So the way I'm going to do that is if it gives me little f and I'm finding an antiderivative, I'm going to go backwards to capital F. So what I'm saying here is this is the function whose derivative would be cosine x. And so what I have to do is I have to kind of train my mind to think backwards. So if I know derivatives, I now have to work backwards to figure out these antiderivatives. So what I'm going to say to myself is the derivative of what is equal to cosine x? And the answer to that would be sine. Right? If I were to take the derivative of sine x, I would get cosine x. And then what I'm going to do again is make sure that I put plus c, because I want to say that there could be a constant as well. If I were to take the derivative of what I just wrote down, the derivative of sine x is cosine x, and the derivative of the constant would go away, and I would have this function f of just cosine x. Okay, number 2, the antiderivative of 1 over x. So this one's kind of tricky. It doesn't necessarily follow some of the rules that we think of when we start doing derivatives. Recall that the derivative of the natural log of x is equal to 1 over x. And then again, I'm going to put plus c. And lastly, we're dealing with a power function, x to the third. So if you think about doing derivatives, whenever you deal with a power function, you end up subtracting 1 from the exponent. So if I'm going backwards, what I'm going to do is I'm going to add 1 to the exponent. Now, if I just said, what's the derivative of x to the fourth, you would say, well, it's 4x to the third. So how do I kind of undo that multiplication there? I want my constant to be 1. And if I were to do the derivative of this, it would be 4. Right? It would be 4x to the third. So what I'm going to do is I'm then going to put the reciprocal of my new exponent out front. And then if I think about doing the derivative of this, I would do 4 times 1/4, which would give me 1, which is what I wanted. And then I would subtract 1 from the exponent, which would give me 3. So 1/4 x to the fourth, and again, plus some generic arbitrary constant, c. Okay, so there's 3 pretty basic examples of just thinking backwards, right? Going backwards, doing antiderivatives instead of derivatives. So here I've listed a table, and you could pause the video and look at some of this. But basically it's saying that if we have a function and we want to go backwards to its antiderivative, this is kind of the rule for this. And if you think about maybe going from the right column to the left column and doing derivatives, a lot of this should make sense. So it says if you have a constant out front, that constant will stay out front with your antiderivative. If you have 2 different functions, you can just do the antiderivative of each one of those. This third one is the most important one. It's kind of a power rule. And our power rule is exactly what I just did with that third example. What I'm going to do is I'm going to add 1 to the exponent, and then I'm going to put the reciprocal of that new exponent out front. So 1 over n plus 1, x to the n plus 1, would be the antiderivative of x to the n. And then we get into some of these rules that you probably already are aware of. If you did the derivative of natural log, you get 1 over x. So the antiderivative of 1 over x is natural log of x. You know that the derivative of e to the x is e to the x. So working backwards, we get the same thing. The antiderivative of cosine is sine because the derivative of sine is cosine. However, this next line, if we do the derivative of cosine, we get negative sine. So if we're going backwards, if I start with sine, that means I had to have my antiderivative of that has to be negative cosine, so that when I take the derivative of this, I have negative sine, which would give me this positive sign there. The derivative of tangent is secant squared, so working backwards there. Same thing with the derivative of secant is secant x tan x, so if I work backwards off of that, I get secant x and so forth. And then we get into some inverse trig, which you don't deal with a lot, so these are just a couple of ones to reference if you ever come across that. So those are some general antiderivative rules, but primarily if you know how derivatives work, you should be able to eventually train your mind to go backwards to find what that antiderivative would be. So we're going to look at a function g here. We have g prime. I want to find g. So what I'm essentially doing here is I'm working backwards. And the first thing I'm going to do is I'm going to rewrite my derivative here so I don't have this big quotient going on. Right? So I'm going to rewrite this, and then I'm going to take the antiderivative. So the 4 sine x is just going to stay 4 sine x. And then I'm going to divide each one of those things by x. So 2x to the 5th divided by x would be 2x to the 4th. And then what I want to do to rewrite this next term, I want to think about this as x to the 1/2. And so if I'm dividing x to the 1/2 by x to the 1st, what I would do is subtract exponents, and this would be x to the negative 1/2. And now I'm going to take my antiderivative. So if that is g prime, g is, well, what's the antiderivative of sine? Well, I know it's going to turn into cosine, but remember the derivative of cosine is negative sine, which means that 4 is going to stay out front, but it means I needed to start with a negative cosine so that I end up with positive sine if I were to take the derivative of that. Plus. Now again, when I do the power rule, I'm going to do the exponent part first, and then I'll worry about the constant out front. So I know that this is going to become 5. I'm going to go up a degree, and then I'm going to divide by that new exponent, or I'm going to put the reciprocal of that new exponent out front. I already have a 2 there, though, so that 2 is going to stay. I'm just going to take that 2 and divide by my new exponent. And again, think about doing the derivative of this. I would multiply 2/5 by 5, which would give me 2. And then I would subtract 1 from the exponent, which would give me 4. Same thing for this next term. I'm going to add 1 to the new exponent. So if I add 1 to this, that's going to give me a positive 1/2. And then I'm going to multiply by the reciprocal out front. So I would put a 2 out front. Now, that plus, I went ahead and put a plus there, but that's going to stay a minus here. And again, you could check this by doing the derivative. If you took negative 2 times 1/2, that would give you negative 1, and then subtract 1 from the exponent. So 1/2 minus 1 would give you negative 1/2. And then again, I'm going to put plus c because there could be a constant added to that as well. Okay, so there's our antiderivative. So if we have g prime, we can work backwards and get g. Next example, I'm actually giving you f double prime. So f double prime is 12x squared plus 6x minus 4, and we want to find f. So we have to go backwards twice. And we're going to be able to do that because we've got a couple of pieces of information about f. So I'll show you how to kind of get started with this. The first step would be to go backwards just to f prime. So I want to take the antiderivative of f double prime, and that's going to give me f prime. I'm going to go back one derivative here. And I'm simply going to use my power rule for each one of these. So that's going to be x to the third, and then I'm going to divide by that new exponent, which means I'm going to do 4 there. It's going to be 12 divided by 3. Plus, this is going to be x squared. And then we're going to take our 6 and divide by 2, which is going to give me 3. Anytime that you have a constant, when you go backwards, you just add an x to it. So it's going to be minus 4x. And then I'm going to put plus some constant c. Now I'm going to go back to my original function, f of x. So I'm going to do the same thing. So this is going to be x to the fourth, and then divide your 4 by your new exponent. So that's just going to be a 1. X to the third, divide the constant by the new exponent, 3 divided by 3, that's going to be a 1. Add 1 to my exponent here, that'll be a 2. Divide 4 by 2, that's going to give me 2. Now what I'm going to do here is, this is a constant, and if I go backwards, that constant would become a linear term, plus cx. And then I have to add another generic constant, so I'm just going to say plus d. You don't want to use c unless you use a subscript to differentiate between the two c's, so I'm just going to use d, so it's a completely different variable there, but that is just representing whatever constant I would have going backwards again. Now, this is technically my function f. However, I don't want to have this generic c and d. I want to know what those actual values were. And so the way I'm going to do that is I'm going to use these two pieces of information that it tells me about f. And my suggestion would be always start with, if it tells you what f of 0 was, always start with that. So it says f of 0 is 4. So what that means is, if f of 0 is 4, that tells me that if I were to plug in 0 for all of these x's, I'm supposed to get 4. So what does that tell me? Well, all of these terms that have a multiplication by 0 are going to go away, so that tells me that d is going to be 4. So what I'm going to do now is I'm going to go up and say, well, okay, if I know that d is 4, now I can find c by using my other piece of information. And that tells me that if I were to evaluate at 1, I'm supposed to get 1. So 1 to the fourth plus 1 cubed minus 2 times 1 squared plus c times 1 plus, I know that d is 4, that's going to equal 1. And if I work through that and solve for c, I end up getting that c is going to equal 5, which means, again, I can go back up here and say, well, I now know that c is 5, and so my function f is x to the fourth plus x cubed minus 2x squared plus 5x plus 4. Okay, I couldn't have figured out what those generic c and d values were unless I was given that information about my original function. Okay, very similar question here, but this one's dealing with velocity, acceleration, and position. So just a quick reminder, if you have the position function and you take the derivative, you get the velocity function, and you take the derivative of that, you get the acceleration function. So when we do antiderivatives, we're going to be working backwards. So we have the acceleration function, a of t is 6t plus 4. We have the initial velocity and the initial displacement. We want to find the position function. So if I have the acceleration function, the first thing I'm going to do is do the antiderivative, and if I do the antiderivative of acceleration, that's going to take me back to velocity. So I'm going to make this a t squared, divide by the new exponent, so 6 divided by 2 is going to give me 3. Add a t to my 4, add a generic constant c. If your initial velocity is -6, I'm going to use this piece of information now. If I know that v of 0 is -6, that's going to tell me that c is -6, because if I were to replace my t's with 0, those two terms go away. So because I know my initial velocity is -6, I know that c is -6, I'm going to go in and replace that with -6. So there's my velocity function. Then I'm going to go backwards again to my position function. So that's going to become t cubed plus t squared. 4 divided by 2 is going to give me 2 there, minus 6t. And then I'm going to say plus c again. Now this is a different c, but I don't have to worry about subscripting that because I am dealing with a completely different, I don't have my old c anymore. I know that that's negative 6, so I only have a single c here. And then I know that my position, my initial position, s of 0 is 9. That tells me that this c value is going to be 9, again, because all of those t's would go away if I plugged in 0, which means that this c value is 9, and there is my position function. So I have my position function, my velocity function, and my acceleration function. And if you wanted to check to see if those are correct, and you're pretty skilled with derivatives, just take the derivative of the position, you should get velocity. Take the derivative of velocity, and you should get acceleration. And that would be a quick check to make sure that you are correct. So antiderivatives, we're just working backwards from derivatives. Got to kind of train our mind to think backwards here. But that is our process.